Hello. This lesson is about how multiple forces work together to determine an object's motion, and how we keep track of them using the idea of net force and force pictures, or free body diagrams. So let me show you the lesson objectives. We did this on week 8 of the COVID-19 crisis of 2020. And the first thing we did is we went into Zoom breakout rooms and we worked on a University of Colorado PhET simulation that allows students to add forces, multiple forces on objects, and see their effect. So you can find that assignment right here. And that one mostly seemed intuitive. Students didn't have a lot of questions about that. This second assignment, balanced and unbalanced forces, that's what we spent the bulk of class working on, and that's what this lesson is going to be about. So my hope is by the time you're done with this, you'll have a pretty good idea of how multiple forces add together and how we can do different calculations to relate force, mass, net force, velocity, and acceleration. This video is intended for students who were working on it asynchronously or who missed class for any reason or who would like to review. So the first type of problems we had in class looked like this. And they basically asked what direction and magnitude does the net force have when you apply these 4 different forces to a box. So magnitude ultimately means the size. So forces are vectors, which means they have size and direction, or magnitude and direction. And we can find out about these for the net force by seeing how the different forces compare. The first thing to notice is that there's actually 2 dimensions here. The first is left-right, also called the x-axis, also called horizontal. And in this problem, the x-axis forces cancel. I'm pulling to the left and the right, and we expect those poles to cancel each other out. On my vertical or y-axis or up-down axis, I see unbalanced forces. So there's going to be a net force on this axis. In general, forces do not have to cancel in either dimension. We can have a net force in both. But for the purposes of this unit, which is our one-dimensional force unit, one of our 2 dimensions will have the forces cancel out. So in this case, it was x. So what does solving this look like? You do a sum of forces equation for the x-axis. 4 minus 4, 0. I have no net horizontal force. You do a sum of forces equation for the y-axis. 12 minus 15, minus 3 is what's left over. So my net force is minus 3 newtons, which I could write as having a magnitude of 3 newtons in the downward direction. So if you practice these aren't too bad. We'll do a couple more. In this case, my x-axis forces don't balance, so I expect to have a net x-axis force. In the y direction, they do cancel. So there's no unbalanced up or down force here. So it looks a little different. My net force in the y direction is 0. My net force in the x direction is minus 4 newtons. So we could say 4 newtons left are the magnitude and direction. One more time. In this case, balanced y-axis, unbalanced x-axis, we can say we have a rightward net force of 10 newtons. So at this point, I'm okay showing you what the answer key to the worksheet looks like. I think you need to do this yourself before you look at it, so hit pause if you haven't done it yet. But here's what I ended up with on my answer key. And as we look through these first 6 problems, what we end up seeing is that in 2 cases, number 2 and number 4, we have an object in equilibrium. Most people see number 2 because we're pulling with the same force in all directions, and that makes it obvious that it cancels. Number 4, you want to make sure you see that as well. Although left and right have 7 newtons and up and down have 12, we don't have to cancel in all 4 directions. We just have to cancel in our own dimension. Up is canceled by down, left is canceled by right. So in each dimension, the net force is 0. This object's also in equilibrium. Because we have the equation A equals sigma F over m, we can calculate an acceleration once we know a net force, a sigma F. So you just plug in your net force that you calculated and you plug in the mass of the object, and you can get all of your accelerations. Number 9 was a bit of a trick question. It said, which boxes can we say for sure aren't moving? I was trying to trick you and have you say the ones in equilibrium aren't moving, but all we know is that the ones in equilibrium aren't accelerating. Unbalanced forces don't cause velocity, they cause acceleration. So whether 2 and 4 are objects at rest or objects in motion, we don't know. All we know is that they won't be changing their state. So hopefully that all makes sense, and just let me know if you have questions on that. We also took a look at how accelerations, velocities, and forces work together to cause speeding up or slowing down. So all 3 of these quantities, and also position, are what we know as vectors. They have a magnitude, how large they are, and they have a direction. Contrasting with scalars, things like mass, that don't have a direction. You can say, I live 3 miles west of town. You can't really say I weigh 32 kilograms right. So having magnitude and direction makes you a vector. These 3 vectors, net force, acceleration, and velocity, they are helpful to understand whether something's speeding up or slowing down. So I told students that in these 2 cases, we have an object speeding up, and in these 2 cases, we have an object slowing down. And I asked them to look for patterns. And the first pattern students noticed was that net force and acceleration are always in the same direction. And that's really because of Newton's second law, sigma F equals ma. It's net force that causes acceleration. So the acceleration will be in the direction of the unbalanced force. The other pattern students noticed was that if I'm speeding up, my velocity, acceleration, and net force are all in the same direction. If I'm slowing down, my velocity is in one direction and the other 2 are in the other direction. So I asked students to sketch graphs of what velocity versus time would look like for these 4 situations. And here's what we came up with. So speeding up means your velocity and acceleration are in the same direction. So in the cases where we had that from the beginning, so here's a positive original velocity. I'm starting on the positive y-axis. And I've got a positive slope, so my acceleration is positive. So that's an object that's speeding up the whole time. Of course, the same is true if I'm going the other direction. So here's a negative or left initial velocity and a negative acceleration. This object's speeding up the whole time. In both cases, we're getting our velocity farther from 0. And 0 is stopped, so in both cases, we're speeding. What's slowing down look like? Well, that means you've got your velocity and acceleration opposite. So here I'm starting with a positive velocity and I have a negative acceleration. So my speed approaches 0. At least up to here, I'm slowing down. Same's true in the other direction. At least up to here, I'm slowing down. Of course, once we actually stop, if we continue to accelerate in the same direction, we're going to speed back up. Because for this part of the graph, or this part of the graph, I'm back into this regime. My velocity and acceleration are in the same direction. So these are the situations where somebody's slowing down, stopping, and then going back in the other direction. So we went through those, and I'm not going to necessarily show the answer key to this part of the worksheet because I think you can do those on your own. And again, just get in touch if you need help. The last type of problem we did are these more complicated ones where we really asked you to get at how different forces can change and how that will affect a net force and how that might affect a mass or an acceleration. So I think for this type of problem, I need to do one for you. And then I'll let you do several other ones. So let's do one of these together. So in number 15, we can see that the various pieces of information we can have are some of the different forces that are on the box, a magnitude for a net force, a direction of that force, and an acceleration. And we can also have a mass. So in different versions of this problem, you'll be missing different pieces. Let's do number 15. We know that we have an upwards acceleration of 3 meters per second squared. That tells us a few things. First, if the acceleration is upwards and not left or right at all, that means we don't have a left or right net force. So this 14 Newton force must be being canceled out. So that's one thing we can figure out. We also know that since we have mass and acceleration, we know that sigma F equals ma. So the net force sigma F must equal our mass 5 times our acceleration 3. So sigma F must be 15 newtons. So we can fill that in. So if there's a tug of war going on that y-axis and up is winning by 15 newtons, up must be 15 newtons bigger than down. So that means this must be 45 newtons. So I'm going to let you work through the other ones, and I'll tell you to hit pause now, and then I'll show you what the answer key is. But at the end of the day, this is like a puzzle where you solve one piece at a time, and the whole thing kind of comes together. So hit pause if you haven't done this yet. Here's our answer key. So in this problem, we had to find the net force by looking at the various arrows. So we saw that we had an unbalanced force left of 3 newtons. So then we plug into sigma F equals ma, and we can solve for acceleration. In this one, because it's a downward force, downward net force, excuse me, that means that the left-right forces must balance again. We have the acceleration, so we can just do sigma F equals ma. Excuse me. We have the acceleration, yes, we can use sigma F equals ma to solve for mass. And in the final one, it's a left-right force, so that means our vertical forces must cancel, so I put my downward force as 27. In this case, what was unknown was the net force, but we had the mass and the acceleration, so I could solve for a net force of 8 newtons. And then if I have an 8 Newton net force, that means there must be an 8 Newton difference between my left and right forces. So that's how I got there. These are a little bit tricky, but I'm hoping after this you have a good understanding of how different forces can help move an object in a certain direction or hinder an object's motion in a certain direction. And just be in touch if you need more help.